So, good morning everybody. Thank you for joining us today. What I'd like to go over are the debug features that are available within the Cortex-M processors and really how to get the best out of them. When a lot of developers first come to Cortex-M, they assume that the debug support is via JTAG. While JTAG provides a nice low-cost, inexpensive way to connect to a microcontroller, it really works by simply shifting the instructions into the processor under control. So this means that you can really only get debug information by halting the processor and then using the JTAG interface to interrogate the system using the CPU itself. On the Cortex-M processors, the debug architecture is a proprietary system from ARM called CoreSight. This has independent debug units and its own separate bus around the processor. So this means the debug architecture is able to stay active and can interrogate the system while the CPU is active. So this means we get a lot of real-time information out of the device. It also means that we can put the processor to sleep and still keep the debug architecture alive. So CoreSight also gives you the opportunity for extensive low-power debugging. So within the Cortex processor, there's run control and memory access support. So this gives you much of the features you'd get if you're used to JTAG. However, in addition, depending on the processor you're using, there are a number of separate trace units. So on the Cortex M3, M4 and M7, generally fitted as standard, there are a couple of trace units, the DWT, the data watch trace, that allows you to stream data from the memory in real time, and also an instrumentation trace that acts as a kind of debug serial connection between the application code and a console window within the debugger. So these give you some very flexible way to debug the processor without disturbing its real-time performance. Also on the M3, M4, M7, there's an optional additional trace unit called the ETM, or the Embedded Trace Macrocell. This allows the debug tool to flow out all of the instructions that are being executed along with timing information. So this way we've got extensive information about the actual execution of your code. So those three trace units together give you quite a powerful debug system that's kind of roughly equivalent to a full in-circuit emulator around the mid-90s. However, the cost of such a system is much lower. And in terms of the pinning access to the different trace units, we can establish our simple basic debug control through two pins, the serial wire debug pins, which are a clock and a serial wire connection. To get access to the standard trace units, the data watch and instrumentation trace, we need one additional pin, which is the serial wire out pin. And then if our device has the ETM fitted, we require an extra 4 pins which are used to flow out the instruction information. So altogether we need a total of 7 pins to get a full advanced debug connection to the microcontroller. Now these might be dedicated pins on the microcontroller, or they may be multiplexed with GPIO and other features of the processor. So sometimes, depending what you're using on the device, you can have a compromise in trading off debug pins for access to various peripherals. There's one other kind of debug trace unit that's available on the Cortex processors. This is on the Cortex M0 Plus, one of the smaller Cortex cores, and it implements a different kind of trace unit called the micro trace buffer. So when you use the micro trace buffer, you take a small area of the internal SRAM, and that is dedicated for debug use as a serial circular snapshot trace buffer. So as the Cortex-M0 is running, every instruction executed is recorded into this internal trace buffer. When you halt the code, a low-cost development tool can then download that information and reconstruct trace information within the development tool. So this effectively gives you a zero-cost snapshot trace that can be exceptionally useful for debugging obscure problems during runtime. This approach currently is only available on the Cortex-M0 Plus. However, for the new ARMv8M processors that will be available as standard silicon, I think towards the end of this year, this technique will be implemented on the newer cores. So we should now be able to get widespread access to very low-cost trace. Now, very often when you buy an evaluation board for a Cortex processor, it's fitted with the large standard JTAG debug connector. In fact, ARM provide, or rather define, a couple of small sub-miniature dedicated connectors for CoreSight. These are either a 10 or a 20 pin connector, and they take up a much smaller amount of space on the board. So again, if you're designing your own hardware, don't use the standard JTAG connector, use these smaller connectors. And in particular, if you have a device that has the embedded trace macrocell fitted, always put on the larger 20 pin connector. The first 10 pins map on to the standard basic debug interface, so you can still use a low-cost tool. And if you need to add trace, then the trace pins are available through the larger connector. Very often when a hardware department lays out a board, they always seem to put on the smaller connector. So if you're a software developer, make sure you tell the hardware guys to fit the big connector. Otherwise, it gets much harder to get instruction trace. So if you get an obscure bug or problem later in the project, it gets very hard to get the trace information out of the processor to help you solve the problem quickly. There are a large amount of different debug adapters available. Kyle have their Ulink series, but many other manufacturers provide debug adapters. Within the Kyle, we now have the Ulink Pro, which features high-speed connection to the device and support for all of the debug units. And then there is a Ulink Pro D, which provides the same high-speed connection but doesn't provide support for the ETM. So again, this allows fast download and high-speed debugging. In the very near future, there'll be a new debug unit called the Ulink Plus. This features, again, access to the instrumentation trace, the data watch trace. So again, we get all of the standard access to the debug units, but it doesn't support the ETM. However, what it does include is a number of programmable IOs, like a logic analyzer, that we can use to stimulate our hardware. These are exceptionally useful for testing, and these are controlled by virtual registers which appear as part of the processor. So by writing to these registers, we can set digital outputs, we can read digital inputs, we can set analog values, and we can read analog inputs. It also means that we can use this tool for power management as well, or reading the power that the device is consuming as it goes along. So we can get instantaneous power measurement, but also it will be possible to trace that power usage over time as well. So the Ulink Plus introduces some very interesting features for doing in-the-loop hardware testing and power management. Should be available in about a month to 6 weeks, and again we'll be demonstrating this at a later point. There's also a debug specification within CMSIS, the CoreSight Cortex microcontroller software interface standard. So CMSIS DAB is effectively a block of firmware that will convert a low-cost Cortex microcontroller into a CoreSight debugger. So this allows manufacturers to add a device to their boards to provide a debug port at very low cost. So again, we've seen that many very low cost evaluation boards also feature a debugger. So these are CMSIS DAP. There are also other similar systems like ST-Link, and I think the Sega also provide a similar system. So now the actual cost of getting a basic debug connection is very low. With our 10-pin connector, we basically bring out the 2 serial wire pins so we can establish a JTAG style connection, and then we also have the serial wire out pin so we can get access to the trace units. So this provides us our basic debug connection to a Cortex-M microcontroller. And then within our development tools, we can select the debug access, the debug adapter that we're using, and then we can essentially go and start debugging our code with JTAG style features. Within the Kyle tools, on the left-hand side of the debug menu, there's also a simulator option. This is a legacy simulator. This supports simulation of all of the Cortex-M processor cores, but it also has some legacy support for early Cortex microcontrollers. So this would simulate the peripherals and the interrupt structure of those devices. So this is some of the early STM32 devices and some of the early NXP LPC devices. So this is a very good learning tool, a way to experiment with a Cortex processor without any hardware. If you're interested in seeing how to use this, just raise a question and I can reply back via email. But it's very good for education and just generally mucking around with a Cortex processor. So once we establish this basic connection, within the debug menu, we have several features that are of interest to us. So within the red box, when you are first establish a debug connection, we can open this debug window and the serial number, the core number of the device should appear in this box. So this is a good way to know if you've got a running processor when you're first bringing up hardware. Just plug in the JTAG, open this debug window, and you know if the device is working. If there's nothing in this box, then you have a fundamental problem with the clock crystal or power or something similar. Also, the Cortex processors, their startup on some of them is getting more complicated. There are on-chip bootloaders, etc. So down the bottom here, we have a selection of different connection methods, how to reset the processor through hardware reset line or internal reset registers. So this allows us to tailor how the debug adapter is controlling the Cortex processor at reset. There's also some cache options here. So to speed up debugging, the debugger holds a cache of the code and certain parts of the memory. If you think you've got a fundamental problem, so for example, if you're trying to test an external bus, you can switch these off, and then you know what you're seeing in the memory and debug windows is actually what's on the processor. There isn't a cache interfering. So this again allows us to get confidence about the working of the hardware. And then finally, in the green box, we can see that here we can see that we're successfully talking to the debug adapter. We've got its serial number, firmware version, etc. And the port allows us to select that we're connecting via a serial wire or via legacy JTAG, and we can also set the clock frequency that we want to talk to the device as well. So again, we can speed up the performance by increasing the maximum clock that's available. Once we have these settings, we have a fully featured debugger. So here we have run control, we can set breakpoints, we can single step through the code. And we can also look at memory as well. So we've got memory view windows, we've got watch windows, and we can look at the registers inside the chip. So all the sorts of things you'd expect from a basic level of debug. To support given microcontrollers, there are also peripheral windows that allow us to look in and see how a given peripheral is set up. Now these used to be hand-coded, but with the explosion in the number of Cortex processors available, it just became untenable to design these manually. So there is a standard called Software Viewer Description File, which is essentially an XML file, and this describes the registers and their bit values, and then it describes the layout of the peripheral view window. So these files are generally created by the silicon manufacturers and then can be used by individual tool manufacturers to create these peripheral view windows. So while a developer, you'd never need to work with these yourself, it does mean that when you're selecting a new device, you should expect debug support to be there as soon as the device is released. So it's much faster to create these windows. They're not as clever as the hand-coded ones, but they are available straight away. Okay, that's progress, I'm afraid. There is a similar approach to looking at middleware libraries, that we have a component viewer file. This is a fairly new feature. So here again, this is created by an XML file where we describe the symbol that we want to look at, the variable, we describe its bit fields, and then we describe the layout of the window. And these windows will relocate with the variables as the code is recompiled. So here we can look it into a TCP library, but there's support for file systems, operating systems, GUIs, USB, etc. So this provides you detailed information about what the middleware library is doing as the code is executing. So at a glance you can see if the code is working, if it's configured correctly. It's also possible for you to design these windows for yourself as well. So if you have a complex project that's running long term, you can build one of these windows to describe key variables within your code, and then this can be used throughout your development team. So again, it increases confidence, speeds up debugging your code. Now, to set up the more advanced debug connection, we go back into the debug menu and then enable the trace features at the top. And on the trace port, it's important to note that there are two communications methods of connecting to the Cortex processor. There's the serial via UART mode, and this has a maximum communication speed of 10 megahertz. But there's also a Manchester encoded communication method as well, and this runs to 100 megahertz. So generally the lower cost debug adapters will only support the UART mode, where the more expensive tools support the Manchester encoded mode and effectively can communicate to the Cortex processor 10 times faster. Okay, so it's important to note when you're actually deciding on buying a debug adapter. In this menu, we'd also need to set the core clock frequency as well. So this synchronizes some timing information to the frequency that the processor is running at. Once we've enabled the trace, we can now flow out variable and data information from the Cortex processor into the development tool. So again, here we have a logic analyzer window, so we can look at what variables are doing over time. And when I first saw these, it looked a bit sort of gimmicky, but when you use it in a real project, particularly if you're doing some kind of DSP or data processing algorithm, it becomes incredibly useful. There are also a number of creative ways that you can use it as well to pull out timing information, to view contents of buffers, etc. So again, this is can also look at peripheral registers as well as SRAM and memory registers. Now the second debug trace, debug unit that's within the Cortex-M processor is the instrumentation trace. Now, I said this was like sort of a serial connection between the Cortex processor and a debug window within the debugger. It actually has 32 channels. One of these is used as a public printf type channel. So when we printf from our code, we can write into the debugger. And another one of these channels is used to send kernel information from the RTOS directly up into the debugger. So we can get some deep level of information about how our operating system is running. Now, this setting up the ITM can be a little confusing. First of all, we must make sure that the core clock is set to the same frequency as the CPU. So this is in effect kind of setting the baud rate for the serial communication between the Cortex processor and the debug adapter. Then we need to enable the ITM stimulus port. So this opens up all of the 32 channels for communication. Then the second half is to set up the communication with the ITM within the development tools. So here in the Runtime Environment Manager, we can redirect the standard I/O from a user function where we'd normally write to a UART or an LCD, or etc. But we can redirect that to the ITM. So this now takes the standard I/O channel and moves it from your peripherals up into the debugger. So when we use the standard I/O through printf scanf, we're now communicating with the debugger rather than any other part of our hardware. So this is, again, very, very useful for software testing. We've done a previous webinar with using the Unity test framework. So here we can write tests down within our application, and then we can print out the results directly into the debugger, and then these can be logged immediately to a file. We can also instrument our code so that during runtime we can send error messages or informational messages up to the debugger. So this kind of gives you an application trace. So as the code's executing, you can actually get a feel for what's going on at the application level. And again, the more you do this and the earlier you do it in your project, the more useful it becomes. As I've mentioned, we can also get RTOS information through the instrumentation trace. So within the kernel, again, we're sending messages through the ITM up to the debug tool, which can then display them in an RTOS viewer window. So all of this is stealing some time off the CPU. It is, however, fairly minimal, and you get a huge amount of information. So here we can see how all of the threads are executing on our code, the amount of memory they're taking, and also, crucially, the maximum memory usage of each thread as well. So again, that's very useful to validate our code, even with a basic debug connection and a low-cost debug tool. Within the latest version of the Kyle tools, there's a new debug feature that's been introduced called the Event Recorder. So this works in a similar fashion to the micro trace buffer, that when we enable it, we create a small buffer on board the chip. This is controllable by the developer. And then we can put macros in our code that write into this buffer. Then during runtime, as the code's executing, the debug unit can read this memory buffer and upload it to the debug tool, which can then recreate, can display each of these messages. So again, we have an alternative to using the ITM to get real-time timestamp data out of our application code and view it within the debugger. So these can be simple codes, or they can be text strings, which can then be displayed within the development tool. So the advantage of this is that it has a minimal impact on the execution of the code. and it runs on all of the Cortex processors. So the M0 and M0 Plus can benefit from this, whereas the ITM, the instrumentation trace, is only available on the larger processors, M3, M4, M7. So the event recorder is again a very useful introduction, particularly if you're working with the smaller devices. Within all of the Cortex, well, in fact, within all ARM processors, there is a performance unit. Within the Cortex-M processors, this is a small number of counters that can provide us some low-level information about the execution of our code on the processor. So again, these are enabled within the trace window. Normally you should disable them because the information is sent up to the debugger during execution. So this effectively takes part of the debug bandwidth, so if it can collide with the instrumentation trace information and you can miss some of the ITM packets. So normally you want to have these disabled and only enable them if you're using them for benchmarking, for example. But these counters give you some low-level information about the execution of code on the processor. So they'll show the number of cycles per instruction overhead. So this is kind of wait states where the processor hasn't been given code fast enough, and also execution overhead where we've incurred extra cycles in serving an interrupt. So this can give you some information about how efficiently your code is running on the processor. So it's useful to compare different silicon vendors' Cortex microcontrollers. There's also load and store units, which give you some indication about how efficiently the code is running on the processor as well, or how efficiently the compiler has built that code. So again, it's a kind of a weak indication for benchmarking compilers. More usefully, there's execution trace, exception tracing. So here we can look at all of our interrupts and exceptions, and we can see the number of times they've executed and various statistical information about how those exceptions are running. So again, this is still with a basic entry-level debug tool, and it gives you some information about the loading of interrupts on your system as well. So again, if you trying to do some very real-time code with lots of interrupts, this will show you how heavily the processor is loaded. Now, with the larger debug connector, we bring out the 4 trace pins and the trace clock, and the first 10 pins basically map onto the smaller 10-pin connector. So once we have the trace information, in our trace settings we can enable the embedded trace macrocell, so that will get us instruction trace, and then we can set the trace port up to give us a 4-bit wide instruction trace. The Ulink Pro is designed to run up to 200 megahertz. Typically, however, we'll get to about 160 megahertz. This can be partly due to board layout, but very often the pins, the trace pins that are on the microcontroller simply aren't fast enough to support execution above 160 megahertz. So this becomes a limitation of the silicon rather than the development tool. However, if you're running 160 or below, then you can get full time-stamped trace information. These trace pins are generally multiplexed with GPIO. So at startup, we need to provide a debugger script that will convert them from GPIO to the dedicated trace pins. And these scripts are now starting to be integrated with the device vendor packs, so the tool chain can be automatically configured to set up these multiplex pins transparently. Before, you used to have to manually add in a script file and make sure it's working okay. So this process is being automated and made a bit more seamless. Once we have the trace port configured, we can now get a streaming trace from the Cortex microcontroller to the debugger. So this gives us timestamp, assembly and C-level tracing. And it's important to note that there is no trace buffer within the Ulink Pro. All of the trace information is streamed directly from the microcontroller to your hard disk. So in effect, you have pretty much a trace buffer that's only limited by the size of your hard disk. So you can log massive amounts of information. This is very good for code coverage, performance analysis and other processes that you need to validate the tool. However, if you're trying to debug a specific problem, there are trace watch points that allow you to start and stop the trace at various points in the code. So it means that you can reduce the amount of information that's been recorded in, so you can just look at a particular function or a particular interrupt over time. So very often when you're trying to locate a specific problem, it's being able to control the trace and filter in information rather than recording everything. Otherwise you just end up with reams and reams of information and the problem is buried in there somewhere. You need to be able to shrink the trace down and get directly at the problem that you're trying to isolate. So once we have the trace, we also get performance analysis. So this will show us the execution time of all of the functions within our code. And again, this is quite crucial for validating software. And similarly, we can get execution profiling. So here on the left-hand edge of our C or assembler windows, we can get the time consumed by each line of code or the cumulative number of calls to a particular line. So again, we can find hotspots or see where time has been spent in our code within a function. It's also possible to get code coverage information. So here, when a line's executed, it will be ticked off. We can also see partially executed code as well. And then there's code coverage reporting, so we can see the percentage of coverage within a given function. So again, this is very helpful when you're doing software testing. It allows you to say that you've done complete coverage of your code under test. So that's kind of given us an overview of all of the features that are available within the debugger. And to finish off here, there's just a table that summarizes the features that are available across the Cortex family.